integrate circuits components, inspect the device external I/Os, inspect the device communications, for instance, if they use RF signal over a proprietary protocol, if they perform cellular communication, Wi-Fi, Bluetooth, Zigbee, basically any kind of communication they have might be a security risk there. Also identify the presence of the buggy programming interface on the PCB itself, on the device itself, like UART, JTAG, SWD. Try to extract private or sensitive data from the device. For instance, passwords, encryption keys, and personal identifying information. And verify the susceptibility of hardware attacks, for instance, sidechain attacks, power glitching, and overclocking. So what's the goal of this presentation? Is to present a summary of hardware hacking tools and techniques for security testing. This topic is very broad, so whenever possible I will link to other research talks that cover way more in depth than what I'm going to cover here. So please go check it out. And also I have a lot just by learning from public presentation, public contents that we have available. So that's another reason to check it out. And also show some of real-world vulnerabilities identified by other research related to hardware hacking. Okay, so lab tools. That's kind of silly, but we have to open the device, we have to sometimes assert the device, so screw, drive set, reflow and multimeter orchestration. Sometimes you have to remove chip from the device itself. Multimeter, we have to check the connection. Oscilloscope, sometimes you have to sample a signal very fast so you can see how the signal goes and to understand on the minimum time what's happening on the device. Logic analyzer, and by the way, a lot of these tools have overlap with each other, and there is no just one correct way to approach assessment. And that's kind of the logic analyzer. Sometimes you can use an oscilloscope on its place. But logic analyzer is cool because they can decode the protocol itself and give you information of what's running there. Programmable power supply. A lot of times you're going to remove the chip and you have to power that device on. You have to know exactly what power to provide to that piece of equipment. We use a lot of microcontroller boards and development boards just to communicate using SPI or any kind of the protocol that you might need there. So in that sense, embedded boards also with GPIO pins work on those cases. FPGA device, sometimes when you have an attack that is, you have to control the timing of the attack very precisely. The FPGAs is the most indicated tool. There are some programmers as well. For instance, the JTAGulink is a universal JTAG programming. The bus blast in the middle is the most common use on the InfoSec hacking scene, let's say so. And you can also always use the vendors on programmable device. Other multipurpose components like bus pirate, that's kind of, I think most of the people that comes from the InfoSec start using this tool as their first tool on hardware hacking, just because they are cheap and they can do a lot, but their limitations can appear very fast as well, because you cannot dump a firmware, for instance, with that due to the speed of that device. And here are other boards, HyderBus. It's more or less recently, and they have much more capable IC on it, and so it allows you to perform other kind of attacks. And this, the other one, GasGo, is a tool that is going to have a FPGA and a microcontroller itself. with some voltage protections and configurable volts. So I don't have one of these, but I think this is going to be a very cool one we do have. Other tool, JTAGulator, basically when you have identified some pins in the board and you want to identify which ones are JTAG, use this tool. So basically it performs a brute force attacks on the pins and try to identify which ones are the JTAG parts. Chip Whisper, that is how can I say it will be the default tool to perform glitching and time attacks. You see on this board here, so and it is also a learning platform. I can't find my mouse. So basically on the right, you see that is a part you can detach itself. That's basically a target device. And the part that implements the attack is the left part of it. Basically, you can load programs and learn how to perform a lot of different attacks, such as glitching attacks and time analysis, power analysis, and that kind of attacks. Also, soft-defined radios. A lot of devices are going to communicate using proprietary RF signals. With them, you can collect the IQ samples and try to decode the protocol itself. Sometimes as well, you can, for instance, if the device doesn't have any Wi-Fi connection but does have a cellular, you can use, for instance, the USRP to create a rogue GSM tower. And those are other kind of transceivers because GSP is boring and laborious. You usually can use these kind of the tools here to implement in Python or other language more easily. You basically define for the RTC one, you basically define like the modulation you want, what's the bandwidth, you define the parameters, and they try to demodulate the signals by itself. Bluetooth one is used to perform Bluetooth kind of assessments, so you can basically sniff Bluetooth. Crazy Radio PA, it's a tool that allows you to communicate with, for instance, wireless keyboards. It's similar to RTC one, and of course, Wi-Fi adapters. And also Faraday Cage, because you don't want to create a GSM fake tower in there publicly. Chip Quick, this is a piece of chemical that is used to remove SMD surface mount device from the board. So you can basically remove your, for instance, a flash chip and try to hit it on a flash header. So reverse engineering printed circuit boards. So what's made of the PCB? PCB is basically a layer of solder mask with another copy layer and then substrate. And you can have multiple layer PCBs as on the bottom left. And here on the right is a demonstration of a cutted kind of PCB. And also, it's not on the picture, but on top of the solder mask layer, it's common to have a sealed, sorry. Usually you have the labels on the sink. I forgot, sorry. So the mask would be the answer. Okay, so after you get to the PCB itself, you have to try to reconstruct what was the device schematic, or at least part of it, to have a notion of what's happening there. For instance, what are the ICs that are there? Is there any data sheet on that? How are the components connected? You can sometimes do visual inspection, like try to have a trace or try to take pictures and try to map that. But that wouldn't work with boards that has more than 2 layers, that have many layers, like the example there or this one. So inside the board you have connections itself. If you have a BGA kind of component, you cannot see under it. Then usually that when you have a gas, so I think this is connected here, you can kind of use a continuity test with a multimeter. Silkscreen. So sometimes the vendor are going to be good enough with you, and they're going to put the labels of the pins. So on the left, for instance, the 3 pins marked there, it's UART pins. So basically you can connect and have UART access. On this right board here are the pins for JTAG access that you could possibly use, for instance, to program that device itself. At DEF CON in 2014, Joe Grant made a comparison of ways to perform PCB reverse engineering. Some of them do destroy the board itself, such as sandpaper. Basically, you use sandpaper to try to remove the layers of the PCB and check it out what's inside that. It's a very good talk. I recommend you to watch it. I'll have a link later here. And in my opinion, the best ways nowadays to perform non-destructive PCB reverse engineering would be using X-rays or CT scans. Here is an example from Joe Grant. I can't see my mouse. Okay, there you go. So basically he used a CT scan, capture a lot of images, and then use the CT scan itself software in order to see the layers. I don't know if that's visible there, but should soon appear here. So that would be the first layer of the PCB using a CT scan. You can track the layers. If you continue to see deep layers, you're going to recover yet another layer of PCB. So the problem with this method, I mean, it's amazing what you can do with that, but it's not everyone that has access to a CT scan. And usually when you do like a black box kind of testing, I mean, that would be ideal to perform black box kind of testing, because sometimes you only have one device, you cannot destruct them, so the only solution for that would be CT scan. Here is another example. Vlad Sabaka presented this technique at Recon in Canada. So basically he used an X-ray machine to identify where the pins are. The TDI pin from JTAG wasn't exposed on the top layer of the PCB. So basically he drew down the access to it, so he could have access to the JTAG pin on this board. Here are some references. I will give the link to the talk later, so basically you can just click on it and see the information from its source of these techniques. Identifying signals. The first thing, like, if you open the device itself, you try to track the communication, how they are interconnected. The next step would be to pick up all the components identifiers and try to find the datasheet of that component. For instance, here's an example of a STM32 controller. You can see that you have serial debug on it. You have UART ports, you have SPI, SCAN interface. A lot of those ports are like configurable, so it's not necessary there, but it's nice to know which pins are what. If you continue on that device, you can basically see the where, for instance, the program pin are present. For instance, PA13 would be on the top left. Okay, but you could easily identify where it's supposed to be and try to track that trace. It's also good to have a notion of what kind of bus protocols you might expect. For instance, the UART usually use only 3 pins. JTAG used to program device. You usually have like 4 pins and have a chained kind of bus. SPI, you have a master, usually the microcontroller, and you have a lot of slave devices that you communicate to, and etc. There are much more kind of signals. So connect to the pads. Okay, so if you identify the pins and you want to try, I don't know, maybe to interact with that chip itself to extract the memory, or make sure what you have there is the protocol you are expecting based on the datasheet and specification and device functionality. Maybe you want to use a logic analyzer on it. So on the left are the probe hooks. There are some that are very expensive, like $100 each probe, but they can pick up very thin pins, in that case, the pitch, in that case. For SOIC, kind of SOIC package device, you also have these test clips that you can plug it on the top of the chip and then expose the pins. Sometimes if you don't have the pin, or if it's very thin, you have to use flying wires and solder on the chip itself. Logic analyzer. So basically, once you've identified the pins, you want to know what is inside that signal. So you can use a logic analyzer to try to decode. And here is an example of using a logic analyzer. Some of you guys might be familiar with that. So basically here I'm saying I want to interpret this code as E2C, and then on the bottom right you can see the commands to decode the device itself. A lot of that is trial error, so you have to be persistent and try to identify what signal is it. Here's another example. This is the JTAGulator tool. This tool basically brute force the pins by trying each combination of the pin as that functionality. So basically you can have like 16 pins that you think that might be a JTAG port, and use a tool such as the JTAGulator to brute force them. You basically just try to use that. That is 2 modes on the JTAG. One is IT code scan, and the other is bypass code scan. What this tool does is like just try to use the clock as clock, the TMS as TMS, and you send bits. If you send bits through the TDI pin. If you receive it back on TDO, you've found the JTAG port. And that's a very nice tool. Some references here, again, like go direct to the source of this information. So the creator of the JTAGulator explains that very in deep. SIGROC also has a list of the decoders and comparison of probes that you can use to connect to PCBs and ICs on the device. Senrio has a really nice blog explaining JTAG in details. So dumping flash memory with SPI. What's SPI? Basically, it's a bus. You have those signals that you expect, and you can connect probes to it and use microcomputers such as BeagleBoard, Bus Pirate, or microcontroller. You can interact with the hardware in several ways, and basically you can dump the content of that flash chip. Sometimes it's not possible to read the flash if they are in the circuit, that's because you are providing power to that chip and also other components. When you try such a connection here, you might power on the microcontroller itself, and the microcontroller might try to read the chip itself. So sometimes you have to put the microcontroller in reset mode so this attack can be performed, or in some cases you have to desolder the chip and read this memory separated. Another way to recover the contents of the flash is basically to just use a logic analyzer, keep sniffing that connection, capture all the commands, and use a tool such as Sniffing that is able to recreate the content of the flash itself. That is a problem though, because you cannot be sure that the microcontroller running as it is would access all the memory, so you basically want to have on your sniffing capture the commands of that part. Some ways to cover the most of the memory is to try like rebooting the device or performing a firmware update. That increases the area that you are going to be able to recover. Dumping flash memory from the bootloader. A lot of embedded devices are going to run Linux on the device itself and use U-boot as its bootloader. So on the left I have like a kind of a layout of a flash device that's common on Linux device. Usually you have a first stage boot that you call U-boot, that you call the run disk, that you load the Linux kernel, and basically the root file system would be on the GAFF2 partition or a squash file system. But if you have access to the U-boot, U-boot has sometimes great commands, for instance the memory display command, that you can use that to dump the flash from there. And also sometimes you can modify the Linux boot parameters. So basically you can say, please don't boot the Linux on the default mode, but put it on the recovery mode. So basically you have root shell access to the entire device. Okay, so you capture the memory. What do you do with it now? Well, the flash memory might be the firmware image of the device, might contain encryption keys that might be shared among several components. Sometimes you can use that to also attack other commands from the network, for instance. A lot of us now have a lot of smart devices at home, and several of them connect to our Wi-Fi. What are you going to do when you dispose those devices? Sometimes the credentials to your Wi-Fi will be present on that device. Some device might have cloud services keys, for instance, to send logs there. And if those are shared among other customers, maybe you can read data from other customers, if that's the case. And again, often by compromising a local device, an attacker can obtain information to elaborate further attacks. Example, get credentials to SSH or cannot on other device. Another tool used to perform firmware analysis is binwalk. Basically, you can point to that firmware image. They are going to check several file header signatures and similar kind of signatures, and they are able to even extract those images. For instance, on the bottom, I have an example of using binwalk against a firmware, and it was able to identify the header of the MTD block, some compressed data, could be the kernel or something like that, if that's on that device. And the most probably the squash file system is the root file system on that device. So let's talk a little bit about hardware attacks, time-based sidechain attacks. So imagine that you are running a microcontroller that has this following code. What's the problem with this code? if you check the lines that are highlighted right now, the device is going to return as soon as the comparison is not right. That will cause like some less instructions should be executed. And basically, if you are doing monitoring, for instance, with chip whisper, you can see the difference of how many shards you have corrected. So when you have 3 corrected, you see the spike there. When you have 4, you have 4. And basically with that, you can brute force 1 shard at a time, using only the feedback of time-based attacks. Side channel leaks. Please check it out. The Colin Flynn, DEFCON talk. He's the creator of Chip Whisper. It's amazing too. And also the tutorial on how to use this tool. Yeah, and how to perform this attack. Other kind of attack, power analysis attack. There are 2 different ways to perform that. One is simple power analysis. Basically, you monitor the device current, how many current the device is using at that time, and sometimes you can make a guess what operation the device is doing, because like different opcodes on the processor have different power consumption. For instance, add, the assembly instruction add would usually use less power than multiplication, for instance. Differential power analysis is similar, but in this case also the attacker, and usually these are used on more advanced attacks, but basically the attacker can control the data they send, and based on the difference of the data they send, they can try to guess which key the device is using by doing the power analysis. So for instance, let's recapture what's RSA. RSA encryption is basically in its core, it's just an exponential operation using a modular number, as you can see on the left. So basically, if you want to encrypt to someone, you're going to use the public key and the mod n to implement that. And that person, in order to decrypt, are going to use its private key and be able to recover the message n. Turns out like exponentiation is very expensive for the processor to perform, but there is a way to perform it more easily, and basically this is the modular exponentiation of large numbers. The idea of the algorithm is like this top right here. For each bit of the exponent that you have, if that bit is 0, you just make it to the power of 2. But if that bit is also 1, you also multiply by the number that you are exponentiation. Let me go to another. Also, as I explained earlier, different instructions execution consumes different amount of power. If you can tell the difference between a multiply operation and exponentiation operation, you can recover the exponential used on the RSA algorithm and then recover the private key. That's an example. Like you always have to power the device. To perform the power of 2 of the device. But when the bit is 1, you also multiply. In that example, it's just an illustration. You have an operation of a power of 2 and a multiplication. And then just a power of 2, just a power of 2, and a power of 2 and a multiplication. Basically, with this kind of leak, you can recover the bits basically the exponent there. And here is a real, I got this image from Wikipedia, but I guess it's a oscilloscope image here. So where to learn more about it? Again, Colin Flynn has a great tutorial on that in detail. Please go check it out. there. Getting started with SPI is a very good resource to learn that. The live overflow channel, that is a capture the flag kind of competitions that is related to hardware hacking. Basically, you have to solve first some challenges online. They usually happen one time a year. And if you classify on the top 500, they will send a board to you that you have to perform hardware attacks on that device. The live overflow channel have created a lot of write-ups on how to solve them. They are very good to see. And also the Wikipedia page explain very good there. Glitching attacks. So basically when you have a glitch attack, you want to perform an operation or modify the environment that the system is executing against what is recommended by the vendor. For instance, you can try, if the vendor says your clock has to be, I don't know, 10 nanoseconds, what happens if you do it in 1 nanosecond? For instance, power. What if in the middle of operation, you just remove the power of that device? Some vendors have on their datasheet, should be thermal, sorry. What are the range of the temperature that the device can work, and also radiation. Well, this can have several effects, such as you can change a value in the memory, you can make up the processor skip an instruction, or basically you can make the processor execute an invalid instruction. So here is an example of clock glitching. Modern architectures have a pipeline, so basically you are going to load the first instruction on the first cycle, and then on the second cycle you are going to load the second instruction and execute the first one, and so goes on. But if you perform a glitching attack, like on the left slide, basically you are going to shorter part of the clock, and that might be enough for the processor to jump an instruction. So basically on the right, you load the first instruction, then try to load the second instruction, and because the clock was very small, the processor couldn't execute the first instruction. So basically you jumped one instruction, and that can result, so that's an example code. That would be the Linux authentication, but basically if you have UID 0 and would fall on the false operation, you don't have to authenticate itself. What happens if you can jump that if on the assembly level? That's the target that usually you try to perform with clock glitch attacks. VCC glitching is similar to clock glitch attacks, but basically instead of shorting the clock, you just cut off the power to the device itself. So the power pins, you connect it directly to the ground, and the device will have less power to execute. You do it very quickly, otherwise the device is going to reboot. And with those kind of attacks, it's similar to the clock glitching attacks, but with this kind of attack, for instance, you could make a memory read operation to return an invalid data, or to not perform it at all. And that can cause all kind of fun stuff. Again, SPI Whisper for that. Also check out the Black Hat Europe 2015. There are some guides of practical electrical glitch attacks, and also the SPI Whisper wiki that are really amazing. So some real world examples. And that's it. So January this year, Marcan, Hector Martin, and there are some technologies that we just take for granted that's secure, right? Like, there is no way a computer using a TPM device to encrypt, like with BitLocker, to have a vulnerability. But it turns out that if you sniff that connection using a logic analyzer, for instance, and recover just 32 bytes of that communication, you can reconstruct the bitlocker key and basically decrypt the hard drive. So yeah, and there are other kind of attacks as well, like maybe you can extract the key earlier, wait some time, expect that hard drive should be disposed, and then with that key you can decrypt the data, for instance. That is a very nice write-up on how to perform those kind of attacks, but the history is if you are using TPM as a mitigation for full disk encryption, and also the thread model is a little bit different, because if you just have access to the PC and you boot it up, the device is going to boot, but then you don't have a credential to log into the device. But for instance, usually computers now have secure boot. If you try to boot a Linux image on it and try to access the hard drive, the TPM won't unencrypted because you didn't boot from valid UEFI. And sometimes you cannot even boot from UEFI. And if you remove the hard drive, it's encrypted. So that's where these kind of vulnerabilities are cool, because you can recover the key and use that on another computer to decrypt that. Ledger Nano. December last year at the Chaos Communication Congress that happens in Germany, Thomas Roth, Dmitry Nedosfasov, and Josh Tato presented research on cryptocurrency wallets, hardware wallets. So basically there are 3 or 4 vendors. Their product is supposed to be very secure because people are putting a lot of Bitcoin money and rely on the security of this device to not lose the money. So they have a very good design itself on the product security. For instance, the Ledger, they have a separate chip with secure functionalities like a secure element, and they have put some thoughts on it. So even with a product that has been designed to be secure, turns out that have vulnerabilities. An example of vulnerabilities that has happened, basically you can bypass the Ledger Nano security because, so STM device, you can protect some memory regions, and what they do is to protect the top 8,000 high memory. That's mapped to the flash. But turns out that the model of STM32 device they are running also have a lower memory address that is not protected, and it's also mapped to the flash. So basically by accessing this other memory that's not protected on the STM32, they were able to modify firmware and put their own software on it. Also, there was another version of the Ledger that has a screen, and while they were doing the PCB reverse engineering, they've seen a very long trace that has a very fast signal. Well, what's that? So what's that? That's basically an antenna. And turns out that they were able to see what key press the user was doing on the screen just by using a soft-defined radio. That was a very good attack. Other attack on the Trezor, not the Ledger, that is another vendor. They had JTAG disabled on that specific device, but by doing a glitching attack against the STM32, they were able to enable JTAG. So please go check it out. That's an amazing talk, what they did there. Another example, Mousejack vulnerability. Basil Thread Research Team has discovered that a lot of those dongles, like Logitech dongles, but really there are a lot of other vendors, in those cases they are not using Bluetooth, had some kind of vulnerability on the radio frequency communication. And basically you can buy like a $33 kind of device. You sniff for the network In some cases, you are going to be able to see the unencrypted traffic of those devices. And sometimes you can inject fake keys on that. And with that, for instance, if you are targeting an organization that use Wi-Fi keyboard and that is some user logged in, you can make like execute a PowerShell script and compromise that machine. So it was a very cool result. That is a list of the affected device, but there are several. It is like Dell, Logitech, Microsoft, and several others there. And basically that was more a vulnerability on the chip they were using to perform the radio transmission. This attack doesn't affect Bluetooth keyboards, but that doesn't mean the Bluetooth is any better. Yeah, okay, I like this talk. How to learn more? Check out security conference talks about hardware hacking. They have very good information on what's going on, what are the new attacks, and basically to keep learning more. During this talk, I have listed some of them. Please go check it out. If you have an old electronic device at home, getting this, well, that is a good opportunity to practice some of these techniques. There are some competitions related only for hardware hacking. One is the Hiscrew Hack Me. I'm not sure if they are going to have this competition this year, but if it does, you have to solve some challenge, and they are going to send you a board, and there are like, I don't know, 30 challenges on itself from a lot of topics such as glitch attacks, power analysis, recovery encryption keys. They are very cool. And just in case, like if you don't want to play but want to learn more, search for write-ups of those challenges. They're cool. There is also this website, Microcontroller, from Matazano. Basically, that's more software-related security, like memory exploitation, such as buffer overflow, and those kind of attacks. But the idea is that you have a lock to a home, and you have some access to it. You have to send commands to, basically to send malformed inputs in order to, even without knowing the code, you open the door. It's very cool. Other option, buy a chip whisper. They have a target just attached to the main attacker device itself. You can practice with it. So I think it's that. Questions? Hello?
Can you sign non-disclosure agreements and confidentiality agreements with some of the equipment makers so that you don't have to go through all this reverse engineering? They can just provide you the documentation.
So this presentation, I focused on the technical details just because we cannot disclose the information of the assessments we do at Mayo, right? We do have, we perform those kind of assessments for other companies' medical device, but we usually ask them to buy by themselves, go to a third party, perform this assessment, and if possible, share the report with us. A lot of them, when they do that, they don't share, so we are kind of don't know what kind of vulnerabilities they have, and yeah, I think that's it. So in the end, we do a lot of assessments on medical device by ourselves. Look.
Without being specific, has there been any devices used within Mayo that you've had to have them stop using?
Tricky. So what I say is that we've assessed some device that, and or not really medical device, but more related to protected medical device, and they saw that like as the best piece of equipment that are going to protect everything. But when you see the device it's supposed to protect, or flow of vulnerabilities. So we recommend the practice not to buy it or not to use that because of those vulnerabilities.
Yeah, on the part of reverse engineering, Do you use any kind of software to keep track on the design of the things?
So good question. Actually, I'd love to have a software. You mean on the PCB reverse engineering, right?
Yeah.
So there are a lot of talks like on how to perform like kind of automate this process by taking pictures or using CT scanners. Personally, even to create this automation, and I mean, there is no off-the-shelf kind of tool for that. Maybe, I don't know, I'm not aware of any of them. So, and it would be very intensive just to create such a program. Yeah, we usually just do that manually. And if I have any suggestion, please. Yeah.
How do you decide where to start when you start looking at a device? Like, do you have a set protocol of steps you go through, or how do you pick?
So I think it's more related to a threat model. You create a threat model before and try to check those threat models. If you just go by, I'll try to reverse engineering every single line of the firmware, you're going to spend so much time. And usually you don't have this kind of time because you have to do other assessments. So we test target attacks on it based on the interface they have and such information.
Thank you. Any more questions? All right. Let's thank Danilo one more time.
Thanks so much. So the slides are available here. You can also scan the QR code if you want. Also, that's my Twitter account. It's been a long time since I tweeted, but who knows? Thank you. Thank you.